Beyond the halo of the Milky Way, on the distant edges of the universe, massive stars are collapsing and new black holes are formed. Beams of intense energy shoot into space, marking violent eruptions from billions of light years away.
Something that happens somewhere in the universe in an observable way about once a day, but it's quite possible that it's occurring much more often than that.
There was a gamma ray burst recently that was about 2 billion light years away, if I remember correctly, and it actually affected the Earth's atmosphere so that people monitoring radio wave transmission in the atmosphere noticed that something was wrong.
They're enormous explosions. They're a billion times as powerful as a thermonuclear bomb.
It's just the biggest explosion that you can possibly imagine, and then some.
They're shockingly powerful events, the most energetic, brightest objects in the universe. The entire energy output of the sun is basically given up in about 10 seconds.
It's something that happened billions of years ago. It's just taken so long for that light, for that cataclysmic event to finally reach us and make its presence known. And when it does, we only have so much time to try to understand it before it goes away.
Mysterious gamma-ray bursts, or GRBs, were first detected in 1967, and by the early 90s it became clear they originated outside the Milky Way galaxy. GRBs were difficult to study because the actual events are brief and occur without warning in apparently random locations. Today, scientists and students, professional and amateur astronomers are working together to solve the puzzle of gamma-ray bursts with the help of a satellite called HETE, the High Energy Transient Explorer.
HETE is a small satellite by many measures. It's small in physical dimensions, it's small in mass, and it's small in dollars, and it's small in the number of people who are actually involved in working on it. But the thing that it's really big in is in terms of its impact that it's had on the field.
The whole gamma ray burst field is really coming into its own because it has these interrelationships with cosmology, because the bursts are so distant. And that relates to the first generation of stars, which relates to how the galaxies and stars were formed in the early universe.
They actually light up the galaxies where they occur, and they also light up the galaxies that are on the line of sight between us and the gamma ray burst. And we can actually study these extremely distant galaxies by the light of the gamma ray burst.
And the reason you want to be able to find the galaxy of the gamma ray burst is so you can study the environment that it actually occurred in. You can find out what kind of galaxies they come from, what regions of the galaxy, how old is the galaxy, what's going on there.
Data from bursts detected by HETE suggests that various classes of gamma-ray bursts exist, and that long bursts accompany supernovas, the implosion of massive stars. Inside the stellar core, a swirling cauldron of burning gas erupts, converting matter into gamma-ray energy. The star implodes, forming a spinning black hole. Powered by the spin and renewed fusion, focused jets of radiation pierce through the star's surface at velocities close to the speed of light.
We do not understand very well how it is that a star could manage to make an explosion this intense, but they do, so there's some physics there to learn. And in physics, we often learn things from looking at the most extreme phenomena, and this is an extremely extreme phenomena.
It's always important when you're studying a new area to find examples that are extreme in some way. Like you want to find the ones that are closest, the ones that are brightest, the ones that are furthest away. That's why it's so important that we get as many events as we possibly can.
HETE is the first satellite to provide and distribute accurate gamma-ray burst locations within seconds, allowing ground-based telescopes and orbiting observatories to analyze the bursts and their afterglows in a range of wavelengths.
HETE is able to look at a large chunk of the sky, and Chandra's fields of view are very tiny compared to HETE, so it would be impractical to use a massive experiment like Chandra to find gamma ray bursts. Chandra is one of NASA's great observatories, like the Hubble telescope. So you only want to use Chandra when you know it's going to work, because the time is just so incredibly expensive and so valuable.
So the thing that's unique about HETE is that we sized the spacecraft to the actual mission. You don't need big instruments to locate gamma ray bursts. They are extremely bright in the gamma rays, and an instrument this size is plenty to detect one. HETE is about 30 inches tall, and it fits into a 19-inch cylinder when the solar panels are folded up, and that has to do with the available space on the rocket to launch it.
Fins unlocked. Fin sweep on my mark. 3, 2, 1, mark.
The ride on the rocket is very rough. It gets shaken pretty hard in some directions, so it all has to be built so that it can withstand that shaking, not have a cable break loose or something like that. So on the one hand, it's something you treat very carefully, and on the other hand, it's actually a pretty sturdy piece of machinery.
Confirm, go for launch.
Drop on my mark. 3, 2, 1, drop.
Pegasus is away.
All safe and arms are armed.
HETE was built by the MIT Center for Space Research under the NASA Explorer program, in collaboration with Los Alamos National Laboratory and institutions in Japan, France, Italy, India, and Brazil. The suite of instruments on board allow simultaneous observations of GRBs in gamma rays and soft and medium X-rays.
Here's our model. We actually use this, by the way. This tells us, how things are oriented, and yeah, the computers certainly know how this is, but sometimes you want to check the computers and make sure they're giving you the right answer. And so having this nice labeled model tells you which piece is where is very useful when you're actually operating the satellite. But these are the solar panels, and these point at the sun to charge our batteries. And then at this end, we have the instruments that actually detect and locate the gamma ray bursts. These are always looking away from the sun. So when we detect a gamma ray burst, it's in the dark part of the sky, in the night sky, where optical astronomers can go and look for it.
HETE circles the globe every 95 minutes, flying at about 17,000 miles per hour, transmitting a data stream to burst alert stations along the equator.
And it's flying 600 kilometers above the Earth, which means that it can be received with fairly unsophisticated receiving systems. We just got a Rand McNally atlas and started looking for places where there was land, where one can conceivably put a receiving station that was connected to the internet. It would start off with Galapagos, and then it would have the Cayenne station, and then Natal, Ascension, Gabon, Malindi, Bangalore, Singapore, then followed by Bohol, then there's Palau, and then Kwajalein and the Marquesas. Oh, we should also put in Christmas Island, which is somewhere out in the Pacific.
If you have a ham radio that can listen in the VHF band, which is above FM, your FM band runs up to 108 megahertz, so this is about 30 megahertz higher. If you have a radio that can listen to that, and if you go to the equator and tune in, yeah, you'll hear something that sounds like a computer modem. Radio HETE, and most of the time it's just got a diagnostic message. But when a burst goes off, it's got the brightness of the burst and the position in the sky and that information.
Time is of the essence when studying GRBs. When HETE detects a burst, information is immediately relayed to the Gamma Ray Burst Coordinates Network, or GCN. GCN members include professional and amateur astronomy organizations and institutions around the world that are ready to do follow-up observations.
When the real spacecraft data come to the ground, the data containing the burst, humans and ground software can look at the data and see whether there's more information to be extracted from it. The computers on board are 20 megahertz computers, and they just can't be loaded down with all the processing algorithms that we can do on the ground. And we all have our own personal set of screens that will allow us to see the health and also communicate with other HETE members who are also watching.
You can feel the energy when you find your burst and you publicize it. But you're not always sure that this observation is going to be able to happen right away. So you're kind of keeping your fingers crossed.
For those few seconds after we send out the alert, we are sending it out to the whole global community. And it's really impressive how the global community does respond.
There's a tremendous immediacy to the discovery of one of these events. For example, on the March 29th event, we were so excited because, immediately from the signals that we got from HETE, we could tell this was a very special event.
There's a burst.
We were going to have to pull out all the stops we could in terms of making sure that all the measurements that could be made on this event were made as quickly as they could be. It worked out beautifully in terms of the total coverage that we actually had.
Amateur astronomers are now starting to consider gamma ray burst afterglows, optical counterparts, to be targets of their searches, because on July 25th of 2003, we detected a gamma ray burst. But unfortunately, all the major telescopes in the world were tied up on a burst that we detected and distributed 2 days earlier. Very few people, if any, looked at the July 25th burst, except for one Belgian astronomer in South Africa who pointed a 12-inch telescope at it and found the optical counterpart. And I think it's good for the AAVSO and for amateur astronomers in general to know that they can go out and actually make a contribution.
And the other aspect about it is because it is a communal thing, there's a willingness to share information that's really at the heart of the culture of science. And the fact that whether what language one speaks or what culture one's from is of less importance than the quality of the ideas.
The HETE mission has opened the door for continued research in gamma-ray astronomy and related phenomena, and has expanded the global community of GRB enthusiasts. Today's students may be the scientists of tomorrow, who prove existing theories and develop new models on the cutting edge of science.
Every gamma ray burst model requires a black hole. So this whole field is sort of predicated on having black holes. And the discoveries that have been made here have only been made in the last 3 to 5 years. So to speculate beyond the next 10 years is almost impossible.
There's still a lot left. People have no idea why a lot of this stuff is happening. And it's kind of funny sometimes in astronomy how little people know and how little you have to observe to make a new discovery.
Most students are up through high school and college are presented with questions that are, either it's homework or it's a test question. But often the really interesting stuff goes beyond the question. That's the kind of extra thinking which leads to places where people haven't been before. Because after all, if you're just answering a question that somebody else has thought out for you, you probably won't find anything new. But there are things all around us which have been lying there waiting for somebody to think a little bit harder and discover.
The whole aspect of going above the Earth in complex machines and trying to do very, very technologically difficult tasks. It's a different type of journey. People are always making that first step, and scientists do that in the course of their research.